Te cuida, ¿no? Te dar golpes, te cuida. Mira, Pablo. Yo también. Escuchante. Es una buena Hombre, sí, por lo que eso sí.
Buenos días a todos. Voy a hacer una breve presentación en castellano y después la charla seguirá en inglés y será grabada. Entonces, bueno, queridos decanos de ciencias, don Manuel Chicharro, quien se unirá a nosotros más tarde, si es posible, vicedecano de Investigación, Innovación y Transferencia, don José Luis Pau, que sí está con nosotros, que todos lo conocéis, queridos compañeros. Comenzamos hoy el ciclo de seminarios de formación del Departamento de Química, Física y Aplicada. Como director del mismo, lo primero que quiero es agradecer al decano Manuel Chicharro y al vicedecano José Luis Pau toda la ayuda que nos han prestado. Sin esa ayuda, este ciclo de seminarios que comienza hoy y terminará en junio no hubiera sido posible. El ciclo de seminarios de Química, Física y Aplicada constará de un seminario mensual, cuyo día se irá anunciando un mes antes, y terminará con unas jornadas tipo simposium de transparencia del conocimiento, el último viernes del mes de junio, la jornada completa. En las jornadas de transferencia del conocimiento, los profesores de nuestro departamento y algunos otros invitados presentaremos la investigación que el departamento defenderá en diferentes congresos durante el verano. A estas jornadas estáis todos invitados. Finalmente, te doy la palabra al vicedecano José Luis Pau, por favor.
Pues muchas gracias, Juan Carlos. En primer lugar, quería agradecer al Departamento de Química, Física y Aplicada por la iniciativa. Me parece que este tipo de iniciativas son altamente necesarias en la facultad y en nuestra universidad, porque, como decíamos antes, pues entre otras cosas, hacen piña. Aparece dentro del departamento, ayudan a la formación de los estudiantes de doctorado o máster, incluso grado. Yo creo que deseable siempre implicar a los estudiantes desde las etapas más tempranas de su formación. Y luego la importancia que tiene también por el carácter multidisciplinar o del enfoque que se quiere dar desde el departamento, ¿no? Que también nuestra voluntad debe estar en colaborar con otras áreas de conocimiento y, por tanto, pues, extender un poco los seminarios o conferencias a líneas o ámbitos de trabajo con los que no estamos habituados. Creo que es bueno. Y en ese sentido, pues agradezco a Juan Carlos la iniciativa. Sé que va a trabajar con la escuela de doctorado también, por darle un poco de trabajo en la acreditación y todo esto. Y poco más. Le agradezco a Juan su presencia hoy aquí con nosotros y le doy la palabra a Juan Carlos para que pueda presentarle adecuadamente.
Gracias, José Luis. Allow me to introduce you our speaker, Juan Cabanillas. Juan is a group leader and assistant research professor of the IMDEA Nanociencia de Juan campus. He has a very extensive research curriculum. Juan Cabanillas graduated in physics at the University of Santiago de Compostela in 1999. He got a PhD in physics from Imperial College London, working with physics of conjugated polymers with Professor Donald Bradley. In 2009, he was appointed Ramón y Cajal Fellow at the IMDEA Nanociencia, and his expertise is extended to a great variety of topics. Among them, conjugated polymers, photonics, fluorescence, chemosensors, fabrication and characterization of polymer waveguides and laser resonators. The talk for today is going to be entitled Boosting the Stimulated Emission Properties of Host-Gas Conjugated Polymer Blends by Disruption of Exciton Transport. The format of this talk is going to be a seminar type, so you may ask any question anytime you wish. Please feel free to ask any question. So please welcome Juan Cabanillas. Thank you so much.
I'm also honored by the fact that I'm the first to deliver this cycle of seminars. Thank you. So what I was planning to do today was essentially to first introduce a little bit the group and the research activity, but this is going to be quite briefly, okay? Just tell you a little bit about the topics we are working in. And then I will pass on to basically laser emission properties of conjugated polymers, which is a project that we've been working in the past 3-4 years. Okay, so I'm working in the Nanociencia, 500 meters, 400 meters away from here. Probably have been there or you heard about it. It's an interdisciplinary institute. There's actually many researchers associated to this university. It is located on the other side of the campus, and actually, a day like today, if you look to the north, I get this beautiful picture. This is something I always like to show whenever I go the road, because I like to do a little bit of advertisement of Colmenar Viejo, which is the place where I live. And I think this is very timely, because today probably the mountains are covered of snow. Probably the rest of the year are not like this, but today probably they will be like that. The institute has a series of research programs, about 10 different research programs. And one of them is time-resolved optical spectroscopy. So it's basically the technique as such, addressed to a wide different type of systems and carried out by different PIs. I am one of them, okay, but we are probably from up to 5 PIs working in this research. So this is a picture of my group. Actually, Jorge graduated already and left, and now we have 2 other new guys that came in. But we are essentially a small group, let's say, working in a research line which deals with mainly these 3 concepts. We are spectroscopists, so it means that we do our own setups. Laser spectroscopy setups. We look into materials, so we have collaborations with different people that know how to do the materials, and we try to establish a relation between the material structure and the phenomena, the dynamic phenomena that we are interested with. And we are also with one foot in optoelectronics, because many of the materials that we are looking at have applications for optoelectronics. Well, so we work a lot with organic molecules and conjugated polymers. And one big block of the activity that we carry out deals with solid state light emission, so materials for light emitting devices and for laser cameras. Okay? So we work with polymers which have some specific features in their structure. These are, for instance, self-threaded polymers with polycyclic side chains.
that are basically devised in order to suppress interchain interaction in solid state. So as such, they are really very nice materials to process in thin films, and you get very high light emitting properties, very interesting emitting properties. We work also with organometallic compounds. Particularly, we have a collaboration with the group where we look at compounds that have copper-1, which are very interesting because they have a property that is called thermally activated delayed fluorescence, which means that essentially these are materials that where singlets and triplets can coexist at room temperature. And that's interesting for OLEDs because charge recombination in OLEDs builds mainly triplets, right? So you want triplets to be emissive as well as singlets. So these are very interesting materials for this sort of technology. And then we are also working with other systems like polycyclic aromatic compounds, nanographenes, etc. We have a second block of activities which deal with metal organic frameworks. So again, we don't do this sort of materials. We have collaboration with people that devise them. And we are pretty much interested in luminescence for sensing. So we basically look at properties in situ upon gas exposure. We can monitor in real time changes in absorption, luminescence, etc., that we can correlate to a specific interaction. And more recently, we have started to work with protein media as well. So we are very interested in proteins which can be functionalized with very small metal nanoclusters. By small, I mean between 8 to 10 atoms of different metals. So typically, we are working quite a lot with gold. Why they are interesting? These metal nanoclusters exhibit properties that is called giant quantum confinements. They have luminescent properties very similar to models. You can use them, for instance, for bioimaging, but you can also think about them to other sort of applications more proper of molecules. So in this field, we are doing spectroscopy, and we are also doing a little bit of photonics. For instance, we can develop protein films with structures, photonic structures on top, and we can look at the emission properties, which are all hidden by these structures. Right. So I'm going to talk today about polymers for lasers. I'm starting for the very, very basic stuff. What is a laser? A laser is nothing else but a medium which exhibits optical gain in a cavity defined by two mirrors. Okay, one with slightly higher reflectivity than the other. So if I perturb this medium, either electrically or optically, what I get is that I promote electrons from lower energy levels to upper energy levels, and the medium emits light. And the photons, which are emitted, are confined in this cavity. So every time the photon passes through the medium, we can either promote the absorption of another electron or can stimulate the emission of a second one. Okay? And this is called stimulated emission. So if I keep strong enough the system, I might have many electrons, much more electrons here than in the ground levels. And that means that stimulated emission can overcome absorption losses and get optical gain. So eventually I can get laser action out of it. Molecules are very interesting for lasers, and you might not be surprised by this because probably some of you have worked before with dye lasers. They were some of the first lasers to be developed. And the reason why they are interesting is because they present a so-called four-level laser system. So the idea is that the initial perturbation promotes electrons high, in high energy levels, but then you have a very fast pumping down to the lowest excited states by thermal conversion and vibrational thermalization. And this typically extends maximum to 1 picosecond, a bit more, but not more than that. Okay? And then once you have the electron on the lowest excited states, it can emit to the manifold, vibrational manifold of the ground state. And the point is that this stimulated emission, in principle, does not face competition from absorption from nearby molecules because these vibrational levels are empty, are not empty. The idea is that you have predominant of stimulated emission simply because you cannot promote electrons from these metals, right? Well, this is general for organic lasers. Organic solid-state lasers, the same concept, are in solid state. So we have beams on a cavity. Eventually, you can operate them by optical pumping. So far, you cannot operate them by electrical pumping, and that's because of a series of reasons that I will not get into. Okay? But we can discuss it toward the ends. And they are mainly interesting, in my opinion, for two reasons. One is that because they are organic, they are molecular based, they have very interesting mechanical properties. So you can develop, for instance, microstructures, microlasers, with very simple methods, okay, with soft imprinting technology, which can also be scaled up. And the other is the fact that you can also functionalize the molecule to tune the emission in a wide color palette. But there is an intrinsic problem of organic molecules for lasers, and is that when you have a solid medium, you start to have also disorder. Okay, you get molecules nearby, you can get different statistical distribution of chromophores, and that means that your line shapes get broader, inhomogeneously broader. And that means that the absorption tail can eventually get into the spectral region of luminescence, and you get self-absorption. So one way to overcome this problem is to use post-resonance energy transfer. Okay, so if, for instance, you have one molecule that emits like this one in the green, you can shift. You see, you get a very large self-absorption, but you can shift the emission of the molecule away from the absorption by doping the film with the second molecule, where the absorption is located precisely overlapping with the emission of the first one. This way, you can shift efficiently the emission from the absorption, and on top of that, you can also promote emission because you are diluting the second mode. Okay? So this is a strategy that has been followed by many groups, and also we have worked quite a lot with lens coupled by post-resonance energy transfer for lasing. Right. So at this point, I will get into the matter. These are basically the two characters of the story I'm going to tell you. So this is called polyfluorine. It's for people that work in semiconducting polymers or optoelectronics, it's a very well-known polymer because it can be processed into thin films with very high optical quality, and it's a quite decent light-emitting material in solid state. Okay? You can get efficiencies up to 50%. You can also functionalize it with other groups. For instance, you can include a benzothiobiazole on the backbone, and that shifts the emission from the blue to the yellow. And again, the quantum efficiency is not as good as PFO, but it's okay, right? So this one is PFO, this one is Dpto. And the thing about these two is that you can blend one with the other, and because of the resonant conditions, what you get is with very little amounts of FABT in PFO, you will drive very efficiently the emission from blue to yellow, right? That's something you can see also if you monitor the luminescence dynamics of the host DFO polymer. The efficiency is really high. It shoots up to 70%. On top of that, because the two polymers have good transport properties, you can do nice polymer light emitting diodes. But there is an intrinsic fact about this system, which is that in these films with such high photovoltaic quantum efficiency, there is no optical gain. Even if the two materials individually, they exhibit optical gain. So they are laser. Okay. When I put them together, I cannot get stimulated emission. And to understand why, I would like to introduce first the technique that we use in our lab, and I'm going to talk quite a lot in this talk, is transient absorption spectroscopy. So this is basically the concept. You have a primary beam, which you split into two beams. Typically, one of them, called pump, is monochromatic, and you use it to photoexcite your material, your sample. In our system, this has a 120 femtosecond duration. And the second one, basically, that we call PRO, is a supercontinuum. So it's a broad spectrum. Okay? Goes from 400 down to 1600 nanometers. So we delay this flow with respect to the pump, and we monitor the transmission of this white pulse to the sample. And what we get is essentially what you would get in a spectrophotometer. So we get the absorption spectrum, but of the excited states of electrons in excited states, promoting them. So essentially, if you have, for instance, imagine we photoexcite, we have a molecule, we go from ground state, we will see the excited state. Then, depending on which frequency we are probing, we can see, for instance, if we go resonant with absorption, we can see a reduction in absorption because we are bleaching part of the model. This is called ground state bleach. If we go resonant with emission, we can see a stimulated emission. And if we go resonant with absorption, excited state absorption, we can see excited state absorption. Okay. And typically, we can observe excited state absorption from singulets, but also from other electronic or species that you put to generate. For instance, if you have a fast persistent crossing, you can see excited state absorption from triplets. Or if you have, let's suppose, intermolecular species such as charge transfer states, you can also see this picture. Okay, so altogether is summarized here. This is what you get. It has a certain broadening, and this is a typical transient absorption spectrum at a given delay. Okay? The idea is that we change the delay between the two, and we monitor the evolution of these different absorption bands. This is a little bit how the setup looks like. Some technical details. Just briefly to mention, we have two independent systems, so we can monitor in the visible near infrared or UV visible. Right. So now let's get into the problem. So if I make a film of the blue and green polymer, yeah, suppose 10–20% of FABT in PFO, I perform such experiments. This is what I get for different delays. So if I go to the region of emission of FABT, which is where a stimulated emission should be located, what I see is that it is dominated by negative change in transmission, which means excited state absorption. Okay? And this is connected to what I was telling you. This system do not exhibit stimulation. And the reason why doesn't exhibit stimulated emission can be understood if we look only at the blue emitting polymer. When we perform the same sort of experiments, we can see that we have a positive region of stimulated emission and two well-separated spectral regions of excited state absorption. One that evolves very quickly, like this, the green trace, which basically matches with the blue emission part, and this is essentially excited state from singlets. And another one which is much slower. Okay? And this longer decay caused by the fact that in the film we are generating also charge transfer states. So the original neutral states dissociate because they found lower energy sites where they can separate in what we call a polar lone pair. All right? And this has a much longer kinetics. So in summary, if I autogenerate a residual of this long-lived absorption species, this absorption will overlap with potential stimulated emission from Dpto, and that causes the loss of stimulated emission. So that was qualitatively, and we can look more quantitatively to the problem, because transient absorption is nothing else but an absorption experiment. So therefore, the signal that you are detecting is given by the Beer-Lambert law, right? So it's the product of concentration, time-dependent concentration, and cross sections. So in principle, if one knows the cross sections of the different excited states, we can obtain the time-dependent concentrations. The problem is that we don't know beforehand this cross section. So we have to reconstruct this cross section, and in order to do that, what we normally do, that we perform this sort of experiments in solution and in solid state. When you perform these experiments in solution, essentially you are isolating what we call intrachain species which are located on a single chain. When you aggregate the system and you look into the properties of the field, you observe additionally contribution from species which are stabilized between different chains, such as polar lone pairs. So by performing both experiments, we can disentangle one contribution or the other. On top of that, we can also introduce boundary conditions. For instance, the fact that the total initial concentration is equal to the total number of absorbed photons, which is a rough approximation. And if you do that, you can basically obtain the time-dependent concentration. Okay? So this is one example, for instance, of a three set of measurements of the same system, pumping with different energies. But you see the noisy curve is the experimental data with the singlet contributions in black and the polar contributions in red. Okay? So we do spectral reconstruction, forcing to fit all the data set, which are about in the order of 50 different time frames for 3 different pumping. So when you do that, you can obtain the time-dependent concentrations. These are given by 2 different energies. So if you want another way to see it, we can obtain the polar pair absorbed photon. Okay? That's 2 different energies. And as you can see, in this polymer, we form already this species, these polar pairs, on very fast times in the past duration. Now we come back to the problem. We want, so the problem is we have these systems with these species, and we want to avoid them in a way. So is there something that we can do to the polymers that we are looking at to avoid this the formation of these polar pairs? So in order to find a solution, we have to understand how polymers are formed. And essentially, I told you already, the main mechanism of formation is given by diffusion of the singlet and encountering of low energy site where a charge pair can be stabilized. Okay? This is one of the mechanisms. And on top of that, when you pump high in energy, you have also large probability of collision, okay, of what we say annihilation, single singlet annihilation, and the formation of upper line energy levels, which can dissociate with much higher probability. Okay? So putting an excess of energy can essentially increase the rate of this process. So if you think about these two processes, in both of them you need diffusion. The exciton has to diffuse in order to dissociate. So one way, for instance, to avoid this problem would be reduce conjugation length. So we try to verify this hypothesis by looking at three different oligomers of this polymer with 3, 5, and 7 units, and we perform the same sort of experiment. So this is on a 7 unit, heptafluorine. These are just taking, for example, as an example, all 3 time frames. Okay, but the results are taken to the complete data set. And as you see, you have also still a very large concentration of polymers that you are generating in the parts. But then you start to reduce the chain, and you can see that the concentration reduces. You have small concentration at 80 nanojoule, but then at 3 with the fluorine trimer, 80 nanojoule disappear. You get that fast transient signal here that the modeling interprets as a fast charge recombination, and then no polymers at all this time. So really using short units help to solve the problem. Okay? Right, so we do these short units, these trimers, and we blend them with the yellow polymer. And we try to understand whether this time we get stimulated deletion or not. Okay? The absorption and the photoluminescence. And if you do a pound product measurement, this is what you would get with the long chain. So you get positive change in absorption, which means cyclic state absorption. You go to the same region, and you can see that as you go from 0.5 to 5 picoseconds, you have a change in signal, meaning stimulated emission. So it really works to disentangle the stimulated emission of this problem. You can fix the detection here and monitor the kinetics. These are taken for different concentrations of FABT in the trimer. And what you see is that you get always an initial positive signal, meaning excited state absorption, which is very fast depleted by stimulated emission. You can now reduce the concentration. If you reduce the concentration, the thread rate is going to be slower. That means this build-up takes longer. And at some point, if you go from 5% to 1%, you no longer see a change of sound, no longer have stimulated emission. So in a way, this is verifying this picture, where essentially this is the host polymer. And what you have is the interplay, the balance between these two different rates. When we have an efficient energy transfer, and observe where the emission from FABT, if the transfer is not fast enough, see the formation of a problem. Okay? This is just to show you that after finding this, we were also looking and investigating other sort of short units that they also work quite well. They were very stable. These are synthesized by our collaborators in Nanjing. And then the next step was, let's make lasers out of them. They have stimulated emission, they should work as a laser system. So how do we make lasers out of them? I told you about what a laser looks like, cavity, 2 reflectors. This is a vertical geometry, but what we normally do in our labs is what we call a horizontal geometry. So essentially, we have a substrate. On top of this substrate, we introduce, we do a patterning. We introduce a grating, okay, and then we coat this grating with the polymer layer. And when you do that, if you design precisely the grating, you can force the different orders of diffraction. For instance, the second order to travel horizontally, okay, and to reflect back and forth on the groups. So essentially, you get a sort of mirror inside the field. Okay, this is it works as a cut. So when you do that, you can basically pump it, and depending on the different separation of the groups, you can obtain emission in different spectrum. You can tune from 540 up to 580 nanometers for the green emitting blends, and this is for the post polymer only, okay, for the 3 units. Okay, so it works quite well. We get also nice optical gain coefficients, much higher in the blends than in the pure films. Also very stable properties. Everything works quite well. Just to show you a little bit in more detail how we do some of these substrates. So we can either work with rigid substrates, so groups done on silicon dioxide, for instance, or we can replicate these molds with PDMS and do soft imprinting into cellulose. Okay, so either with one or the other, you can get groups with different separation, which diffracts efficiently. We normally work with the second order diffraction order because we don't need very short distance between the pitches. Typically, we work between 280 to 400 nanometers pitches separation, and these correspond to a picture of such lasers on cellulose acid. Okay, these are, for instance, 3 different polymers with emission in the blue, green, and red, and polarization properties. They are linearly polarized, and something you can do is that you can, because they are plastic, you can bend them, and you can see a slightly shift of the single modes of emission upon bending. Okay. This was a parenthesis how we make this sort of government. And now we come back to the problem. So so far I show you that reducing the chain length can help to avoid polarons. Another question is there something we can do on long chains, some structural modification to achieve also the same result? So initially we were thinking about the long chains and the possibility to introduce statistical conjugation breaks to get a sort of polymer made out of different oligomers. But this turned out to be a little bit difficult from the synthesis point of view. So another approach we tried was to introduce twisting units. So what happened is that these fluorine units typically are a little bit steric, and in solution they do not like to twist very much. So that, in a way, when you process that into a film, you get sort of planarity. Chains tend to form planar regions, planar domains, okay? Where chain packing is very efficient and you can get strong interchain interaction. So by introducing these the new units in 1, 2, or 3 number, we can increase the dihedral angle, reduce molecular packing, and the original idea was perhaps that helps to reduce the formation of phase. These are the guys. We call them 1 pH, 2 pH, and 3 pH. The first thing we did was to look at the energy transfer process, and they work quite well as we expected, simply because by introducing 1, 2, or 3 units, we don't observe strong changes in the photoluminescence properties. Spectrally, they look pretty similar. They have also very nice quantum efficiencies, range from 82% to 63%. The transfer rate was very high, almost 1. So principal, good conditions. And then we took these polymers, we blend them with FAPT once more, and we tried to understand if they have optical gain. So this time, what we did was to do what we call amplified spontaneous emission measurements. So the idea, this is a conventional photoluminescence experiment, but the idea is that rather than exciting the film with a circular spot, we excite it with a narrow stripe, and we collect the emission wave-guided at the edge. If the wave-guided mode is amplified, what you should see is a narrowing of the line shape, because you are only amplifying that mode with respect to the complete photoluminescence. And as you see, it didn't quite work for the first blend, 1 pH with FAPT. It worked with 2 pH FAPT. It didn't work at all with 3 pH FAPT. This is a spectrum taken with the maximum fluids that we have available with ablation. What you have here is basically for the green blend plots of the fluid width maximum as a function of fluids, showing how narrowing takes place and how also the emission undergoes a change of slope above the threshold of amplified spontaneous emission. So it worked, but only for 1. And then the question was why it works for 2 pH, not for 1 or 3 pH. So again, we came back to transient absorption experiments. These are transient absorption spectra taken at different delays for blend number 1, number 2, number 3. And you probably don't see very well the difference, but the main difference is here. If you zoom up here, you can see that in the region of interest, you have for the second blend stimulated emission. For the first blend, you have a sort of mixture. And for the third blend, you have only excited state absorption. Okay? Same thing if you monitor the kinetics here. You only see a change of sign for the second blend. So this is just corroborating what we saw before. There's only stimulated emission in the second blend. But then we try to understand a little bit why, and we perform global fit analysis. So the idea is that we propose a series of differential equations, coupled, and we try to fit a complete data set in order to find an agreement with what we measure. Okay? So it turned out that this photophysical model fit pretty well with data. So essentially, this involves photoexcitation of a singlet state. And then we have a branching. We have the possibility that this interacts with a second singlet to lead to annihilation and form polar pairs, or the possibility to transfer efficiently the energy to FAPT. These two photophysical pathways, for 1 and 2, are in different amounts included in the 3 different blends. These are the equations. Correspond to the. This in case someone was sleeping. Corresponds to basically the model I showed you. These are basically the results. This is the experimental one. This is the reconstructed matrix. And what does it mean, all this? Well, essentially, we have decay associated spectra for the different contributions that we get, singlets in the host polymers, singlets in FAPT, and substructure states. But the main point is that we obtain the rates for the different species and also the annihilation rate. And the main difference is here. You compare these 3 different rates, there is a large difference between the second blend, the first, and the third. It's much lower, more than 1 order of magnitude, almost 1 order of magnitude in some cases. Okay, meaning that there is a connection between the disappearance tolerance and the reduction of annihilation rate. Okay? So in a way, what we are proposing is that by isolating chains, by reducing this mechanism of annihilation between singlets, we can reduce the probability of emission of polarons and effectively obtain stimulated emission. Okay? So in a way, this strategy of introducing twist units work, but we don't really have a full answer why it works for 2 units, why not for 3, for instance. This is still an open question. And this is the end of my talk. I don't know if I have extended a lot.
It's fine.
So in a way, having a material with a high luminescence quantum D is not enough to fulfill the requirements for a good laser material. This is probably one of the conclusions that I want to. And this happens in polymers, but it can be extended to many ones. You have to take into account other contributions, such as excited state absorption. And in these polymers, in particular, the presence of charge transfer states, polarons, and even triplets can, in some cases, jeopardize this dye amplification process. So you need to find strategies to turn a little bit around. Okay, so that's it. I just want to thank, these are the 2 guys that really did the work. They were former students in my group. They are both back to China. Sen-Sun did mainly the work in the long chain polymers, and Yan-Chi was working mainly with the ongoing collaborations in IMDEA and external collaborations with a big emphasis on my collaboration with Professor Guidon Xia in Nanjing, with whom I have collaborated for almost 10 years, and she has sent me a lot of different polymer materials. And thank you very much for your kind attention.
Do you have questions? Yes.
Interaction, through one polymer, like inside.
It's a complete disorder system,
Okay.
which we normally make these things by dispersing, by forming first master solutions of the two different polymers and blend them together, and then process them into thin films. They are really amorphous, typically. Some of them they have even gas transitions. Happy to be here something. But these are only for the small molecules, but for the polymers as well. They are around 200 degrees. That means that the really principles don't have order, crystallinity. Of course, you can have some sort of short-range order, which is very difficult to assess in our case, because connected to that, structural information is something we lack with this sort of system sometimes. And to understand the different properties of the 3 blends, 1, 2, and 3, would be very useful. The problem is that they are really amorphous. It's really hard to I also forgot to say they are commercial problems. The first 2. Okay? The other ones, of course, they can't compare.
Okay. Basically, I have 2 technical questions. The first one is which laser do you use on the amplifiers on the diffusion setup? Because I suppose it's not the same one that the laser.
Yeah.
And we usually use energy unit.
Yeah.
But for me, I think that it's not the same using because second laser that's good.
Right. It's very interesting. So for amplified spontaneous emission or for measuring laser emission, typically we photoexcite with neodymium gas. And normally pulses which are from 1.5 to 6 nanoseconds, depending on the wavelength that we need. Well, we have, for instance, an oppo, which is 6 nanoseconds, which we can tune, but very often we don't use a simpler neodymium jack, which has 0.3 nanoseconds, 300 picoseconds. So those are the typical systems. So what we are trying to do now is to go a little bit more, stretch it more to the lower end and try to pump these systems with indium gallium nitride laser diodes. So we get an array, we build up at the institute power supply. That's about 700–800 euros, the total cost of the system. And try to pump these systems with sometimes works, sometimes not. So that was one of the questions regarding the laser. And the second one, you are right. It's really difficult to correlate measurements that are done with different pulse ratios. This is it's actually one of the main problems in the field. People measure with all sort of kind of lasers, and the fluence with a femtosecond laser is not a fluence with a. You have to be really careful when you try to quote or refer a value, compare it with another working literature.
And my second question is about the geometry of the laser that you place the array on top of the film. I didn't understand that too well, so if you could repeat it.
Yes. So essentially, we know where our systems emit, and we know where the stimulated emission is located. So if you go to the Bragg law, which is not written here, sorry. Here it is. You know lambda. M is the diffraction order that you want to plot. 1, 2, whatever. And typically, what you want is the diffraction along the plane. Why? Because you want basically to confine the emission on your cavity. Your cavity is your film, okay? On top of this sort of mirror. So this has to be 90 degrees. So if you put 90 degrees here, then the refractive index, you know it, more or less. Then you can obtain this. This is the pitch that you require. So the pitch that you require goes very much with the diffraction order that you want to exploit. Of course, ideally, one would like to exploit maybe the first order of diffraction because you have the highest diffraction efficiency. But the problem is that that requires the smallest pitch, and technically, sometimes it's difficult. It's ratings with 70 nanometers, 50 nanometers separation. We normally go to the second one. So we get this, and then we simply deposit on top the film. If you deposit a very thick film, then there won't be corrugation on top of the film. Okay, and that means that if you have any sort of confinement, it's going to be the diffraction is going to work only at the interface between the substrate and the film. And here you have the lowest refractive index mismatch. So you do not get very efficient confinement. What you get, you try to get is to minimize the thickness in order to cover homogeneously the grating, but at the same time, to have some sort of correlation.
And the pump laser is coming from top of
The pump laser is coming from the top, and the emission is outcoupled perpendicular to the substance because it's second order. If you were using first order, that would be an edge emitter. So you would need to implement the emission detection from the edge. And that's another advantage of using second order.
Thank you very much.
Cristina.
Thank you, Juan. Very nice talk. I'd like to apologize because I'm a theoretician, so maybe my questions are a little bit dummy or anyway. When you explained the experiment of the pump probe, you were playing with the time delay between the both. So the probe is always after the pump has finished, isn't it?
Correct.
So, and you use the time delay just to check what is going on or what is happening afterwards. How can you be sure if after you get your laser off, your pump laser off, a lot of things can happen, especially in these systems that are huge and are thousands of millions of rotational and vibrational states. How can you, do you have any other technique, of course, just to see?
Yes. I mean, I guess, you know, there are several evidence, but one is, for instance, photoluminescence spectroscopy. You can resolve the photoluminescence. Typically, you can observe also, you know, that you have a trace that extends to the nanosecond. But coming back to your question, if let's say, if the study were finished when the probe arrives, ideally, you do not expect a change in transmission. Because what you...
But you can have intersystem relaxation,
but then the probe is not
vibrational.
finished. So if you have
Okay,
intersystem,
okay, yeah,
then
okay.
you still have... Yeah, you can have intersystem crossing and you can have triples. Now the question is, are we sure if we have intersystem crossing? We are sure.
You are sure.
Yes, yes, because we do also measurements of triplet absorption independently. And we don't observe, for instance, I can show you something here. These are very often are questions that we have in the. So we can, for instance, do this sort of experiment, which is CW photoreduced absorption. So with that, what we do is that we freeze the system, we go to 77 Kelvin, and then we photomodulate. So we basically photo excite with rectangular laser shape, and we see the change in absorption. So you can resolve the absorption bands with triplets. You can then compare if these absorption bands are in the pump probe measurement that you are recording. You can, in a way, discard whether you have any.
This is why I find it like science fiction, because I know that there are many states. And if you wait, a lot of things happen between the vibrational states, for instance, or whatever. Because things, and this is why sometimes when you explain these things, I know there are many other details that you don't obviously say, and I miss, of course, and this is why I was asking. Everything, you never play with in gas phase. So all those experiments are liquid and solid.
Yeah, these are films. Of course, we do also liquid. Yes.
Have you ever tried to put a control pulse just to change something of what happened into your system? Do you know these experiments in gas phase in which they have pump, probe, and something in the middle just to control whatever they want to obtain at the end? This is always
whatever they obtain at the end.
There are experiments in gas phase in which they
pump in gas phase, yes, but
not in here.
No, I mean in the gas phase, what we normally do in pump probe is use I guess mass spectroscopy to look at
exactly. This is what
the elements that you observe, so you can actually distinguish very well fragments. No?
Yeah, of course, but in here it doesn't make any sense.
Phase.
Yeah, thank you.
We know it's reversible, so the system comes back originally to the same. So we know that we are not modifying the system with a laser. We have proofs that we don't have triplets, so what we think is the only interplay here comes from singlets and also from polymer. The other thing that I didn't mention is that the time frames that we are looking at are restricted to only 200 picoseconds. Those are pretty short time.
Yeah, for this kind of system. Thank you.
Any other question?
I have another one.
Okay. Go ahead.
How long these lasers work? I mean, because yeah, basically how long they can be working, the laser.
So you are talking about the photostability.
Yeah.
So in many of them, for instance, this guy, this is a matter of minutes. If you are pumping in air, literally for 60 minutes, that's laser emission disappears. Minutes. I mean, it doesn't take long. So in order to avoid this problem, what people do is modification. One modification that we normally do is, for instance, to exchange here and field chains by DRU substituents. That makes a more robust system than what would effectively have. Yet, in general, polymers are quite unstable. Molecules are much more stable. So the ones that I showed you after they are really stable. We pump them in air. Yeah. And we even anneal them up to 200 degrees, just to check the stability, the thermodynamic stability. So polymers tend to be more unstable, but you can devise materials that are quite more photostable.
Another question? A kind of translation. A polar is a radical cation species, right? As well. And you said in the very beginning that that electrical pumping is not working so far. Right? I know that there is some progress in that. Can you please say something about the electrical pumping?
I mean, let's say that the two main problems are the modest charge transport of these systems, because in order to build up population inversion, you need to inject a lot of carriers, which they have to travel and they have to recombine precisely in the recombination zone. And this is one problem. And the second problem is that you have additionally in these systems absorption losses, which arise from triplets, polars, I mean charges. When you inject charges in these systems, they lead to polar absorption. So if you do engineering and you design materials that have this absorption shifted away from the stimulated emission, then you can have some chance. But otherwise, it's really difficult. And to the best of my knowledge, there's only one evidence from 2019 on a really electrically pumped organic laser, but the structure is terribly complex. Actually, I got it here. This is a paper by the group of Adachi in Japan. So what you have here is you have glass, you have indium tin oxide, which is a transparent, semi-transparent electrode. You have a mixed order grating, first and second order of silicon oxide. Then you have this material specifically, which is thermally evaporated, so it's a single crystal. And then on top you have an exciton blocker, and again a second order of a mixed order, really complex, quite hard to be done. And the surprising thing is that since 2019, there have not been more reports from this group or other people with these regarding this. So I have the feeling that's probably quite difficult to, and also the material has to meet really lot of requirements. But I think something that is interesting about this is that you can also pump them with cheap, low-end sources. And this is what we are trying to do, such as a simple laser diode.
Thank you very much. Do you have any other question? No, let's thank again Juan for his
Thank you.
great. Me gustaría, ya que ha llegado el decano Carlos, si por favor quisieras decirnos algo, te cedo la palabra. En un principio os he agradecido tanto a ti, Manolo, como a José Luis la gran ayuda que estáis prestando a este ciclo de conferencias, que tiene una gran producción. Y bueno, pues muchas gracias. Y te cedo la palabra si quieres darnos algunas palabras.
Me puede ser un compromiso porque he escuchado en inglés y mi inglés es bastante pobre, prefiero en castellano.
Sí, sí, porque el comienzo ha sido en castellano, la presentación y la charla. Pues,
bueno, no hay nada que agradecer. Que como decía, me corresponde. Me encanta tener este tipo de iniciativas. Igualmente para física, creo que deberíamos tener este tipo de charlas, conferencias que sobre todo incorporan a nuestro día a día la investigación que ya hacemos, pero no es la divulgación, la conversación, la colaboración y sobre todo buscar sinergias entre otros mundos. A veces conocemos lo que quiero decir arriba, o incluso un departamento que quiero a la derecha. Por lo tanto, verdad que no es un placer. Siento no haber podido llegar y no por teléfono porque tengo que contestar una llamada de evento. Gracias a vosotros, gente de Química, Física, Aplicada. Ojalá que en las siguientes, las salas se vayan llenando, aunque sea de forma lineal y comercial, pero gracias.
Muchas gracias, Manuel. Bueno, pues ahora lo que vamos a hacer es, nos vamos a ir a comer, nos vamos a la residencia de estudiantes. Todo aquel que quiera unirse a nosotros, pues se venga y podemos charlar con más tiempo, pasar un rato entretenido, relajado. Pues gracias a todos por asistir.
Bueno.
Voy a quitar.